so we, one second, sorry, yes. So, so today we have a special guest. We have Professor Allan MacDonald from the University of Texas at Austin. So people working in condensed matter field very well aware of his contributions. He works on diverse fields in spintronics, quantum Hall systems, even Kagame systems, and any exotic systems to talk about, he's there. And most importantly, his contribution in graphene is very well known today. In fact, he has won several awards, but let me focus on some of them. One of them being Buckley Prize, which he won from the APS in 2007. And very recently, he was awarded the Wolf Prize in Physics in 2020 for the contributions in the magic angle graphene, and which we all know now has evolved into a subfield of twistronics. And this is something that I think he's also going to talk in detail today. So with this, let me welcome you, Allan MacDonald, and it's a pleasure to have you here, and we look forward to a healthy discussion.
Okay, thanks, Karthik, and good evening, everyone. As Karthik said, I'm going to speak about twistronics, about the electronic properties of Moiré superlattices, as I will explain. Please feel free to interrupt me with either expert questions or non-expert questions. This talk will be directed mainly to students and non-experts. And it will be drawn from the work of some collaborators, students and postdocs and visitors at the University of Texas at Austin, especially Mingxi, Wei Chen, Jihang Zhu, and Pavel Potash. So this topic had its 15 minutes of fame. Got a lot of attention a couple of years ago, starting from a couple of years ago, thanks to important experimental advances in being able to make Moiré's superlattices that I will explain in a very controlled way. And specifically the realization of bilayer graphene with a twist angle that has a magic value at which we had predicted more than a decade earlier that strong correlation effects would occur. So at the time, people weren't able to make bilayers with controlled twist angles. And this whole subject is really built on the experimental advances. What was seen in those experiments, led by Pablo Herrero at MIT, was that the electronic properties, summarized here by a standard measure of resistance versus temperature and carrier density in a 2D electron system, that many different kinds of electronic states occur over a range of carrier density that is easily achievable with electronic gates. And so I'll talk a lot more about this, but this is really strong correlation physics and ability to change the chemistry of the system simply with electrical gates. And so this is really what started the strong interest in Moiré superlattices. And as I'll mention, this work is still very active and going in many interesting directions. So here's the outline of my talk. I'm going to first make a few general remarks about electronic properties of so-called quantum materials, and then talk about how Moiré materials fit into this landscape, before ending my talk by focusing on twisted bilayer graphene. So here's the theory of everything in condensed matter physics. It's just what you learned in high school, Coulomb interactions and quantum mechanics. Same two ingredients that are responsible for the periodic table and for the properties of atoms. But in a condensed matter system, is a system in which electrons are not attached to individual atoms, but they can move throughout a material. In the simplest case and most common case, a crystalline material. And I'm showing here a two-dimensional lattice, which will figure prominently in my talk. This is the honeycomb lattice. So this is the electronic structure of a single sheet of graphene. As I think probably all of you know, the honeycomb lattice is a simple textbook example of a non-Bravais lattice, has two atoms per unit cell, labeled A and B here, and therefore two sublattices in the crystal. And the special property of crystals that we exploit routinely in condensed matter physics is that in a crystal, because of the momentum scattering is discrete, Bragg scattering off a periodic medium, it means that momentum remains a good quantum number, just like for particles in free space. And that makes, the problem of solving the quantum mechanics for a single electron in an infinite crystal just as no more complicated than solving the quantum mechanics of a single atom. And so here's an example of how energy depends on momentum in a crystal. This is again for a two-dimensional graphene lattice. And I'll come back to this simple so-called band structure, energy versus momentum, again in my talk. Of course, because of Bragg scattering, momentum in a crystal, the momentum space is finite. And I'm showing here the momentum space of a 2D triangular lattice. It's a honeycomb lattice as triangular Bravais lattice. And so energy, one important property of any crystal is its band structure, how energy depends on momentum. And one thing I want to draw your attention to here is a property that applies to semi-metals or semiconductors or to gapless semiconductors like the one like this graphene sheet. And that is that in a limited, if you're only interested in a limited energy range, indicated by my green circle here, then all of the states that are in that energy range are close together in momentum space. And that's actually very important for the properties of Moiré superlattices that I will talk about. Of course, as you all know, the properties of solids go from simple to very quickly to often impossibly complicated once interactions between individual electron degrees of freedom are included. And this picture shows the two energy scales of a typical crystal. There's an energy scale which is the width of the bands of energy versus momentum that I was showing, which is basically the energy scale that electrons get by spreading out across a crystal. And there's an interaction energy scale. And when the interaction energy scale is dominant, that means that when energy varies weakly with momentum, and therefore when electron velocities are slow, then we know from experience that, well, first of all, we know that it's usually difficult to make any rigorous statements from theory about what the electronic properties will be like. And we know from experience that many electron states typically occur in systems in which the interaction strength is large compared to the bandwidth, so-called narrow band systems. And that's, as I will discuss, that's what we can generate at will in Moiré superlattices. So the next section of my talk is going to be about Moiré materials. So these are artificial systems that are formed by making Moiré superlattices, but they're described, at least approximately, by exactly the same kind of model that applies to real materials. So you can simulate real materials, or maybe create new kinds of physics that occurs in periodic systems by forming Moiré materials. And at the end of my talk, I'm going to talk about the specific case of twisted graphene bilayers. Okay, so first, Moirés. Moiré is a standard term in electron microscopy, and for example, and in other fields of physics, and also in describing textiles. According to Wikipedia, the origin of this word Moiré is related to the word mohair in English, which is a certain type of wool. And it's made its way to French and then back to English with an accent. And it's used to describe, basically interference patterns between two different periodic structures. For example, these are Moiré fringes created by simply rotating one layer relative to another, or there are many ways in which you can create Moiré patterns by overlaying two similar two-dimensional periodic patterns. And but the Moiré materials we have in mind are related to a specific type of Moiré pattern. It's the Moiré pattern created by overlaying two similar two-dimensional crystals. And you're looking at an example of a Moiré superlattice, or you're actually looking at a bilayer two-dimensional crystal system. It's the simplest type of Moiré pattern. And this is actually a picture of two honeycomb lattices, one on top of another, and represented by these gray lines that connect the lattice points. And you only see one of the two-dimensional crystals because they're sitting right on top of each other. And but if you twist one relative to the other, then you can see that there's a spatial dependence in the coordination between the two layers, how one layer sits on top of the other. And what you see most easily are the points where locally the two layers are stacked on top of each other, so-called AA points. And if I do this again, you can also see that, in this case, we're just twisting two identical layers. And if the twist angle is small, then the coordination between the two layers changes very slowly. Technically, what you're seeing there and what varies periodically is the displacement of one layer due to rotation modulo the lattice vector of the crystal. And so it produces the periodic pattern. You can see that's called a Moiré superlattice. And what we're mainly interested in is electronic properties. And those electronic properties will see that periodic pattern. And in fact, Let me turn to the simplest example of a Moiré superlattice. This is not the one that was first studied experimentally. That was bilayer graphene, but this is one that is now being studied experimentally. And this is the case of transition metal dichalcogenide two-dimensional crystals, a bilayer, one on top of the other. W stands for tungsten diselenide. M stands for molybdenum diselenide. And these two-dimensional crystals have essentially the same lattice constant. You can change the way one two-dimensional crystal is coordinated by the other by simply, for example, twisting the two layers. So in this particular case, if you look at the band structure of these two-dimensional crystals, you will see that they're semiconductors. And what I've drawn here with an energy axis vertically is the energies at which there are states in the band. So this energy is the top of the valence band in the tungsten diselenide, bottom of the conduction band. And you can see here the type 2 band, so-called type 2 band alignment, where the bottom of the conduction band and top of the valence band are localized to good approximation in different materials. I'm just going to talk about the case of holes in the system. So the holes in the top of the valence band, if you remove some carriers from this 2D system, for example, using gates, the holes would be located in the tungsten diselenide layer. And if you have a Moiré pattern like the one I showed you, then the spatial coordination between the tungsten layer and the molybdenum layer will vary slowly in space. What is shown on the right-hand side here is an estimate that we did several years ago of the energy, how the energy of a hole at the top of the valence band in tungsten varies as you move the molybdenum layer underneath by a certain amount. And what you find is that the top of the valence band, which are electrons on the cation tungsten sites in this material, they're localized on the metal site in this material. And there are two actual two effects that cause the energy of the states at the top of the valence band to vary as you move the molybdenum layer underneath. One is that there's a level repulsion effect that pushes the states in the tungsten up more strongly when the coordination is such that they are more strongly hybridized with the molybdenum orbitals. And the other is a simple electrostatic effect. If the metal sits on a negative ion on the other site, then it will see a repulsive Coulomb potential. And that creates this spatial pattern. Turns out that in TMD materials, the size of this modulation is some tens of milli-electron volts. There are now better estimates of this modulation strength in the literature. And when you have a Moiré pattern, this coordination actually changes slowly on a length of a lattice scale. And the important thing is that because these are two-dimensional semiconductors, the low energy states are very close together in momentum space. And they can only resolve, because their momenta are similar, they cannot resolve spatial structure that occurs on a length scale smaller than the reciprocal of the momentum range of interest. And that means that for the electrons at the top of the valence band, they see for a given momentum. They only see this slowly varying potential, and they're insensitive to the atomic physics. They're actually described by a model of electrons with an effective mass that move in a periodic potential. It turns out there are only, in this material, there are only two states with opposite spin at the top of the valence band. So this system actually, it turns out, maps exactly to free electrons with an effective mass moving in a two-dimensional periodic potential. And the period in space of that potential is the period of the Moiré pattern. And we'll see why that's important. The Moiré pattern in typical experiments has a lattice constant of around 10 nanometers. So in fact, you can think of these as artificial crystals with giant atoms that have a size of about 10 nanometers and are separated by a distance of around 10 nanometers. The reason that's important is because with this huge lattice constant, you can change the number of electrons per effective atom just using electrical gates. Typically with electrical gates, you can change the number of electrons per atom in a two-dimensional crystal by around 10 to the 13 per square centimeter. Other techniques allow you to go somewhat larger, but for Moiré superlattices, 10 to the 13 is plenty. And 10 to the 13 per square centimeter is, let's say, a part in 1,000, 1 electron per 1,000 atoms. With gates, you cannot change the chemistry of a two-dimensional crystal very much. Chemistry depends on number of electrons per atom, but you can change the number of electrons per artificial atom by a factor larger than 1. So you can effectively dope without, by large amounts, without introducing any disorder or any different atoms, and you can do it all in situ. And that is exactly what the nature was of the map of resistance versus carrier density and temperature that I showed you before. As I'll come back to later, the carrier density was being varied by some small integer number of electrons per effective giant atom in the Moiré superlattice. Okay, so I'm not going to talk about this too much, but people are already looking experimentally at this type of Moiré superlattices, which basically maps to a single band crystal, a Hubbard model. There were a bunch of papers published in last year showing interesting properties of these systems, showing Hubbard physics, but also showing Wigner crystal type states at band filling factors, at several rational band filling factors. And those Wigner crystal states, you don't usually see in real crystals. And the reason is, I believe, is simply disorder. So you can see Hubbard model physics. Very recently, there have been a couple of experiments that looked at metal insulator transitions in these systems by tuning the ratio of the interaction strength to the bandwidth. So you can, continuously drive systems through metal insulator transitions and look at fundamental physics questions in that way. And of course, for, as many of you are aware, for a one-band Hubbard model, the key question is, is a two-dimensional Hubbard model a superconductor, as many people have supposed in connection with high temperature superconductivity? And now there's the prospect of answering that question rather definitively just using experiment. I noticed something in the chat here. Okay, I can ignore that for the moment, but anybody just speak up if you want to ask a question. Okay, so in TMD Moirés, the results I showed you were for so-called heterobilayer, a bilayer formed from two different materials. There's, excuse me, there's definitely a prospect for exploring new types of physics in other types of TMD bilayers. The simplest kinds are just homobilayers. It turns out that if they're stacked right on top of each other with close to zero twist, then you realize not a triangular lattice potential, but a honeycomb lattice potential. And honeycomb lattices are bipartite. So they're more like cuprates, for example, and they exhibit different types of physics. And also in these systems, you can hope to look at questions that often arise in multi-band systems in real materials like orbital order and perhaps Kagame physics. And so that's just TMDs. There are many other classes of materials, basically van der Waals materials, where you can realize or hope to realize by using the tear and stack and exfoliation techniques people have developed, that you can hope to realize Moiré superlattices. And I think this subject is just beginning. I'm going to spend the rest of my time, and I think I have about 25 minutes or so, talking about the first Moiré superlattice material, which is twisted bilayer graphene. So I'm coming back here and again showing you this band structure. This is for graphene, energy versus momentum. The low energy states are these blue pi bands, which are odd under inversion in a graphene sheet. And my little circle reminds you once again that the low energy states are close together in momentum space. And that means that if you have some part of the Hamiltonian which varies slowly in space, then it just produces an effective potential that has the periodicity of the pattern of the interlayer coordination and is not sensitive to microscopic physics. Actually, in these Moiré systems at a general twist angle, they're not really two-dimensional crystals if you look at the position of every atom. But the point is that for low energy properties, that simply doesn't matter. So that's, I just showed you single layer graphene band structure. Single layer graphene is a Fermi liquid. It has observable interaction effects, Fermi liquid effects that renormalize band structure properties. In some cases, certain broken symmetry states occur, but basically its properties from the point of view of strong correlation physics are not especially interesting. And we'll see that in the Moiré superlattices, we can get to a case where that's not true at all. It really turns graphene into a strongly correlated electron system. So let's see how we get there. So now I'm showing you a band structure, energy versus momentum, for bilayer graphene with a particular stacking between the two layers. This is for the equilibrium stacking, in which so-called Bernal bilayer stacking, in which the one of the atoms of the honeycomb of one layer is in the middle of the hexagonal plaquettes of the other layer, and one atom is directly above the other layer. So that's the equilibrium structure of bilayer graphene. Main things I want to point out is, if we're interested in an energy range of a volt or so, all of the states are close together in momentum space, as I've been emphasizing. And we can see also here that the two Dirac cones of the two layers in this case are deformed by the interaction between the two layers in a particular way. Turns out the linear band crossing and two of the four states are pushed away from the Fermi level by around a third or so of an electron volt. And so this is because of interactions between the two layers. When you have a twist between the layers, that interaction between the two layers will be present, but it will be position dependent because it's dependent on the coordination between the two layers. And now I'm showing you a figure from a paper that I wrote together with a postdoc, Rafi Bistritzer, about a decade ago, in which we tried to make some points concerning the electronic structure of twisted bilayer graphene. And what this illustration is showing the hopping between one layer and the other as a function of coordination. And in the Hamiltonian coefficient of the term that maps electrons from one layer to the other, it's a complex number. And in bilayer graphene, as I emphasized at the beginning, there are two different sublattices labeled A and B normally. And so that means that hopping from one layer to the other becomes a 2x2 matrix because of this sublattice degree of freedom. And I'm only looking at, this plot only plots one of the components of that 2x2 matrix. And as a complex number, the arrows actually here are, the length of the arrows is the magnitude of the complex number, the strength of this particular term in the Hamiltonian that maps from B sublattice of one layer to the A sublattice of the other layer. And the direction of these arrows is the phase of the interlayer tunneling. Both of these vary spatially with a particular spatial pattern. And one of the main points of this paper was that, first of all, that at small twist angles, you would never be able, there are certain discrete set of angles at which the two layers have a commensurate relationship to each other. Related to that is the property that the spatial dependence of this interlayer tunneling depends only on first approximation that we used in this paper, only on a single number. So the interlayer tunneling Hamiltonian has one parameter that you can determine experimentally, for example, from the electronic structure of the bilayer. And all of this spatial pattern of this particular tunneling matrix element, for example, it vanishes when you have, the fact that it vanishes when you have BA stacking at these set of points that have the periodicity of the Moiré pattern. It's all really just determined by symmetry and by the fact that the two layers are separated by a distance that's larger than the than the lattice constants within the layers, and that property causes everything to vary slowly in space. So the electronic properties of the twisted bilayers depend only on actually one number, which is the interlayer hopping. Really, it's two numbers, the interlayer hopping and the twist, but it turns out that it's only the ratio of those two numbers that matters. And so the strength of the interlayer tunneling basically defines defines units for twist angle. And so if you're the units of twist angle as you like, then there's really no, and for a particular value of this dimensionless twist angle, which you put in the real scale of the interlayer tunneling, which is, as I mentioned a moment ago, around 1/3 of an EV, it turns out that a particular value of the dimensionless twist angle, which in dimensional form is around 1 degree, something magic happens, something that actually, from point of view, and discovered numerically from this model, and that is that at this twist angle, the energy of the lowest energy graphene states, as I'll emphasize in later, there are actually 8 states here, energy depending on momentum. And you can see that the dependence of energy on momentum practically disappears at these magic twist angles. And what that means, of course, is that the electron velocity has dropped to essentially to 0. If you include details, you'll find that it's dropped by maybe a factor of 1,000 or 10,000 relative to the large velocity of the isolated graphene sheets, which give these strongly dispersive bands at other twist angles, particularly at larger twist angles. And only at discrete twist angles does the velocity drop to very small amounts. And so this is the region where it was clear strong correlation physics would occur, and where and being able to actually, in a controlled way, make samples, bilayer samples of graphene with this twist angle is the experimental accomplishment that really opened up this Moiré superlattice field. And a lot of important work there done by Pablo Herrero, but also by my colleague Emmanuel Tutuk at the University of Texas and many other researchers to open up this field. So in my remaining time, and Karthik, jump in to tell me if I'm wrong, but I'm giving myself 15 more minutes.
Yeah, that's perfect.
Okay, I'm going to talk about the two perhaps most interesting things about magic angle twisted bilayer graphene that we're understanding better and better as time goes on. The first has got to do with its topological properties, which manifest in a quantum anomalous Hall effect. And the second, of course, is the superconductivity, which phenomenologically has many similarities with cuprate superconductivity, and maybe a second, convenient experimental example of superconductivity, how superconductivity by critical temperatures can be such a large fraction of bandwidths in those materials. Okay, so topology. I'm going to explain the topology of twisted bilayer graphene by talking about some properties of a simple AB bilayer graphene, which are really the root cause of of the topological properties of twisted bilayer graphene. So what I'm showing here, again, with these two-dimensional vectors are magnitude and direction. And this is on the left, you're looking at the electronic structure of Bernal bilayer graphene. And really, you're looking at how the states in the valence band depend on momentum in a block sphere representation, which shows that these, bilayer wave functions can be represented by a block sphere, and what these arrows are saying is that the electronic states in bilayer graphene are half in one layer, half in the other layer. And the directions of these arrows are the phase difference between the two layers. And that phase difference has a momentum dependence and some topology, which is inherited ultimately, of course, from single layer graphene sheet. And that is that in these actually valley projected bands, I'll come back and emphasize valley again in a moment. In these valley projected bands, the phase difference between the layers winds by 4 pi in momentum space when you go around momentum space, a circle in momentum space. So this is a kind of vortex with vorticity 2 in momentum space of the bands. And so in bilayer graphene, partly for this reason, there's a tendency for, exchange interactions don't like the states to change rapidly with momentum. I think you're mostly familiar with the idea that's responsible for magnetism in metals, that that energy exchange interactions like spins to be important. So they, to be parallel, and they like spins to be. They also like, for the same reason, these layer pseudospins represented by these arrows to be similar to each other, to have a low energy state. They don't like them to change rapidly with momentum. And so bilayer graphene has a broken symmetry state where the pseudospin direction spontaneously twists out of the plane indicated here near zero momentum and goes to the North Pole, which corresponds to polarization in one of the two layers. And that polarization is indicated by the color scale here. And along with that broken symmetry, it turns out, is the gap between the valence band in blue and the conduction band in red opens up. So this is all properties of bilayer graphene that were explored some time ago, and are actually very fragile. In fact, this broken symmetry only occurs when interactions are made stronger by suspending a bilayer graphene sheet and removing the surrounding dielectric material. Similar things happen in twisted bilayer graphene, except that the correlations or interactions are made more important by narrowing the bands. So in bilayer graphene, as you can see here in this cartoon, the block spins that represent, the block vectors that represent the two-level, two-layer system, that as a function of momentum in this broken symmetry state, when you integrate over momentum space, when you cover a certain area in momentum space, then you cover basically the entire northern hemisphere of the sphere. And most of you are aware that, for spins, there's a simple relationship between Berry curvature and Chern numbers and area covered in a Bloch sphere as a function of momentum. And what we know from work on quantum Hall effect, going back to the topological theory of the quantum Hall effect by Thales and so on, that this band structure here, valence band states that vary in momentum in this topological way, actually have a non-zero Chern number. And non-zero Chern number, through the kindness of nature, actually it's an amazing fact, understood since the days of the quantum Hall effect, that a topological index of the band structure is actually easily observable, and because it gives rise to a Hall conductivity. So when you have a gap system and the bands have a Chern number, you have a quantum Hall effect. And what happens in bilayer graphene is that the bands have Hall effects, carry Hall effects. And here I am emphasizing what I didn't hid somewhat so far, is that there are low energy states at two different momenta related by time reversal symmetry in graphene, labeled here K and K prime. Generally people refer to this as valley, valley K or valley K prime. So it's another pseudospin. And so it turns out that, when you have these sublattice or layer polarized states, I should say, then you can do this, for example, as in cartoon A in this picture, simply by adding a gate electric field to push electrons into the top layer instead of the bottom layer. So this state depicted in A can be a single particle state. And these arrows are representing the chirality of the system, the sign of the Hall effect. And what these two arrows are emphasizing is that because these valleys are related by time reversal, when they have the same sense of polarization, they have opposite Hall conductivity. So this layer polarized state A in bilayer graphene has no net Hall conductivity, but there are many other states nearby in energy that either have spin Hall effects or even an overall Hall effect if opposite valleys have opposite sense of layer polarization. Then you get a quantum anomalous Hall effect. So this is the story of bilayer, AB bilayer graphene. There is one very important addition to this story that happens in magic angle twisted bilayer graphene. First of all, let me just emphasize this. So in this density of states plot versus energy are the flat bands of magic angle twisted bilayer graphene. Turns out there's a spin degree of freedom, of course, and there's also this valley degree of freedom that I mentioned. So every flat band comes in groups of 4, distinguished by this spin/valley flavor index. And in addition, there are 2 flat bands, just as there are in bilayer graphene. And when I have a Moiré superlattice, what happens is I have this 4-fold degenerate, now very flat valence band, and 4-fold degenerate, very flat conduction band. And they are separated at the magic angle by a large energy from the so-called remote states. And so we only have these bands. And what that does is it gives us the opportunity to break flavor symmetries and create low energy gap states by placing the Fermi level in the gap between the flat bands and the remote bands for some of the four flavors, and in the gap created at neutrality by breaking this, turns out, sublattice symmetry for some of the flavors. So in this case, these are showing the four flavors. This is actually thought to be the insulating state for band filling factor -2, which means 2 holes per Moiré period in twisted bilayer graphene. And so 2 of the 4 flavors are neutral, have occupied valence empty conduction, and 2 of the 4 flavors have their flat valence band completely emptied in this broken symmetry state. And that possibility of those creating insulating states is in this way by breaking flavor symmetries is special to the Moiré superlattice, doesn't exist in bilayer graphene. Now, if you take that story and you allow different filling factors for different flavors, then if you have insulating states at odd filling factors, then you necessarily have different occupations. You have occupy the these topologically non-trivial valence bands, for example, differently for one valley versus the other. And when you occupy the valleys differently, the cancellation that I referred to before that makes the Hall effect disappear, that cannot occur. So when we have insulating states at odd band filling factors, odd number of Moiré bands completely filled, and then we expect to see an anomalous Hall effect and a quantized anomalous Hall effect. And indeed, that is exactly what was seen very early on by the group of shown to be accurately quantized in later experiments by the group of Andre Young at UCSB. So there's a quantum anomalous Hall effect in magic angle twisted bilayer graphene due to differently occupied valleys in momentum space. And I think I better skip this point. These quantum anomalous Hall states, let me just say without going into details, are perhaps the first example in nature of magnetism spontaneously broken time reversal symmetry that is not associated with aligning spins, but simply to do with orbital magnetism in which electrons move in space with one or the other sense of chiral properties that somebody can ask me about if they like. So let me use my last couple of minutes to talk about clues about superconductivity. And I'm showing you here a typical resistance map versus, in this case, versus carrier density in units of band filling, 0, -1, -2, insulating state I was talking about, -3, also an insulating state. And what you see in this plot is versus perpendicular field are the standard Shubnikov to Haas oscillations, which are a standard way of detecting Fermi surfaces and measuring their size. So that means that neutral bilayer graphene is an insulator. If I start to remove electrons, I can get close to band filling -2, and I'm in a Fermi liquid state. And if you look closely at these Shubnikov to Haas oscillations, it tells you that 2 of the 4 flavors have their valence bands completely empty. And in this region, I have a Fermi surface in the 2 remaining flavors that are gradually being emptied. And this is where the superconductivity occurs. This picture of Fermi surface reconstruction is verified by weak field Hall measurements. The Hall effect, of course, measures the carrier density in the partially filled band and tells whether the Fermi surface is hole-like or electron-like. And so this picture of this region of filling factor between -2 and -3, where the strongest superconductivity occurs, is pretty well established. And it seems like superconductivity occurs in a flavor polarized state, most likely a spin polarized state. And I'm going to skip this. There are interesting analogies between magnetism and generalized magnetism associated with, with spin and valley as generalized spin indices in this system that are echoes of what happens in metallic magnets. But in my last couple of minutes, I want to talk briefly about superconductivity. And let me introduce the topic this way. This is a theoretical model calculation of the resistance of magic angle twisted bilayer graphene in a model in which electrons are scattered by electron-phonon interactions. And this parameter here, R, has to do with the band structure model, the Moiré superlattice model with position-dependent interlayer tunneling that I explained to you before. And one thing I want to mention in passing is that it's clear that our original model wasn't perfect, and that you can refine it by, instead of having one parameter, by allowing yourself one or two more. Turns out that hopping between layers in the same sublattice is a little weaker than between different sublattices. And so there's some uncertainty about the details of the band structure, but mainly actually because of interaction effects. But this kind of picture is qualitatively right. This is what resistivity that you would expect in this system, using the well-known electron-phonon interactions of graphene. And but if you compare that with experiment, then you will see that, first of all, the resistance at low temperatures is much, much larger than you would expect based on the graphene